Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our D programming language series. In today's lesson, we're going to be looking at something really cool and something familiar to you if you've studied algorithms. And that's the idea of memoization and functions. And D has this really cool feature known as Memoize in part of its functional library. So with that said, let's go ahead and take a look here. So what I've got set up here is a little library that we're going to import here called std.functional. In fact, it's actually quite important in the D programming language, which enables some of the functional paradigm features that we'd like to use in our D programming language. So in order to understand this feature, though, there's actually a blog post talking about memoization in the D programming language that's useful to reference. So here it is. And you can go ahead and just search Dlang Memoize if you want to find that blog post, or search the website. But we're going to go ahead and start with the library here. And then let's go ahead and find the functional library here, which should be in std.functional here for our paradigms. And we're going to find lots of interesting stuff here. So again, this idea of currying, partial function evaluation, and importantly, this idea of memoize. Okay, so this idea that we're going to create a function that caches its results for fast evaluation. Let's go ahead and take a look at this here. So with memoize here, and again, you could read a little bit on the Wikipedia page if you'd like here. The basic idea here is that what this does here is we basically create a alias, or one way to do this is to create an alias, so you can have the sort of memoized version, if you will. But anyways, how the memoize function works is it basically says, well, if I have a function and it takes some amount of inputs, so let's go ahead and illustrate this out here. Some function here, I'm just going to call it func, and it takes in some number of inputs, and I'm just going to put ... here because we could have any number of them, and we have a return type, say it's an int here. And we're going to do this expensive computation, but if we know given the same inputs we'll get the same or equivalent output, why don't we just compute this one time here with our inputs and store that somewhere? So effectively what this is doing is creating in a table somewhere func with, let's say if we put in input 1, 1 or something, and this is sort of our key here. Let's go ahead and label it here. And the result or the value, so effectively this might be building a hash table like structure here. And let's say the value is 2 here. And if I call func again, 2, 1, and then let's say we get 3 here. You can imagine this is some, some function or something, but you get the idea here. We just execute this function one time and we get the value. Now, what's going on in the body of this function here? And let's pretend this is, hundreds of lines, of code. And maybe it's really expensive to compute. It's doing some, again, really interesting setup and some expensive computation or whatever. Then, well, we can just avoid that, right? We can effectively just dodge this whole computation here because we have the input and the expected output. Now, this works really well with D when you start adding the pure attribute, for instance, to your functions, because, well, pure functions are basically functions that are supposed to respond to given the same inputs, you get the same output, right? There's not outside mutation from the outside world. So that's the idea. So it might even be interesting for some things like if you are computing sine or cosine, or again, maybe some, interesting mathematical expression to, again, try to memoize it and see if you get a performance boost. Now, internally, those functions tend to get very well optimized. So maybe those are a good example, maybe not. But anytime you're, say, generating some sequence. So anyways, let's go ahead and look at some examples here for memoization here. And we've got a few in the docs. And again, I'm in the Phobos standard library for functional here. And let's look at our favorite Fibonacci sequence. So again, what is the Fibonacci sequence? I'll just go ahead and put it in the top right corner here. This is the idea where if the first Fibonacci number is 0 and then 1, and then to get to the next number, I add 0 plus 1, then I add 1 plus 1, 1 plus 2, 2 plus 3, 3 plus 5, etc. Okay? Now, the typical algorithm for doing this then for Fibonacci, let's go ahead and implement it here. And I'm just going to go ahead and call this fib here. Let's just work with longs here. And let's assume they're going to be positive. So unsigned long fib, we'll take in some value here. And we can write it as concisely. I don't know if you saw it in the help value saying it n less than 2, then what are we going to return? Well, whatever n happens to be. So 0, for instance, gives me 0, 1 gives me 1, and then at 2, well, that's where we need to do some work here. Okay, and I'm using the ternary operator, so this is basically an if condition, saying if this condition, then evaluate here, otherwise give me the next portion of this code here, which is going to be to call fib, and, well, we want the n minus 2 plus the n minus 1 element, right? So to get the, again, this index here, right, we're looking back 2 and 1 element in order to calculate it. Okay, so that was the idea. Let's go ahead and test it out here. And we'll just go ahead and write out the value here. Let's go ahead and do this in 2 steps here. Let's go ahead and just do result equals fib of 10, and we'll write out the result here. Okay, so let's go ahead and give this a run here. See if we made any silly mistakes. 55. Here, let's do a little bit of a smaller number here, like 4, just to make sure that we are working here. And we get a value of 3, so let's see. 0, 1, 2, 3, 4. Okay. And that is in fact giving us 3 here. Okay, so that looks good to me. Then we should expect 5 to then give us 5 here for the 5th Fibonacci number. 6 should give us 8. Okay, so we know we're working here. Okay, so interestingly though, and this is sort of a famous problem, because I'm computing the Fibonacci sort of on the left side and on the right side over and over and over again, right? As I perform this march here, okay, through our numbers, I'm recomputing this, which relies on the previous 2 values, and then, you know, this value which relies on these 2, etc., etc. So this can be quite expensive. In fact, let's see how expensive it gets here. If I go ahead and do like 18, and let's actually time this as well, just to give us an approximation. So this is taking, about 1/4 of a second here. And let's go to like the 27th number. And that's taking, you know, a little bit more time. Let's see, 33rd, just a little bit more. 39th number, now over half a second. And very quickly, we're going to see, even as we just add, you know, one number here, our time is going to soon start getting pretty exponential here, as we're just adding one number at a time here. Okay, so 2.5 seconds. Let's see if we get to 44, and soon it's going to become somewhat unbearable for us to time this here. Let's just do 45, and then we'll call it a day here. But that's a rough approximation, right? We're ignoring some of the overhead, right, to time and you know, compile this program. But 6 seconds for this value. So let's see what would instead happen if I cache these 0, 1, 2, 3, etc. Fibonacci numbers in a table. So again, effectively, it's building this sort of hash table for us. Okay, so let's go ahead and let's just rewrite this function here. And what I'm going to go ahead and do here is just first rename this. Let's call it fib. And there's a few different ways that we could do this. Let's do it 2 different ways here. Let's just call it fast fib here for now, for fast Fibonacci sequence. And we'll bring up our documentation. So that's all I've done at this point here. But we want to actually memoize this. And again, here's what the example we did. And yeah, we should probably add no throw and save here. But all we have to do basically is memoize this with the standard library function that we're given. So that's pretty cool. It's going to build that table out for us and store this. So that's really, really neat here. Okay, so let's go ahead and give that a try. And let's go ahead and not highlight anything. Memoize. And yeah, let's make this nice and large here. Memoize. Okay. And let's keep our previous experiment that we had here. And what we're going to go ahead and do is, let's just make a copy here. And this time, instead, we're just going to call fast fib. Okay. On the same value, 45. Our slow version took, you know, about 6 seconds, give or take. Let's go ahead and see with our memoized version here. And back to 1/4 of a second here. Okay, so that's pretty cool here that we're, you know, really speeding things up here. And actually interesting, that might have been just for the first compile. So we're actually at like 0.006 versus 6 seconds, roughly. So you know, on the order of 1,000 times faster in this example here. Again, if I move out of the way, you can see the results again. So this is really neat. This is a cool feature in the D programming language. I mean, normally how you'd have to do this, right? What you would do, I mean, what this is doing behind the scenes here, of course, is creating and storing somewhere in memory this table here, right? So you would, you know, have to allocate somewhere, you know, fib table, and then take in, you know, in this case, it would just be some index here. This is sort of the signature of what it is. But however many values we want to store, let's say up to 45. And then basically what you do is look up a value here. Again, maybe some of you have done this here. Like, you know, you initialize every value to -1 or something. And if it's -1, then you calculate the fib value and then make use of that. And then go forward. But again, we don't have to really worry about that. We just memoize, save the value here, and it's done. Very clean code. You know, if you need total control, you can still manually create a table that you look up the memoize values, and that's sort of fine, right? Maybe you would use like a nullable type or something of that nature. But overall, this is very clean, and you can see the results again immediately here. Much, much faster and really cool here. Now, the thing that they also did in the, or demonstrating here, is that you can just, you know, basically memoize the entire function here, which let's go ahead and give that a try and see if we get the same results here. Okay, so because that's effectively what we're doing here, we're building the table here. So why not just create an alias, and I'm going to just call it alias, alias fib, and this is going to be memoized here. Oh, memoize. There we go, autocomplete. And this is going to call fast fib. Okay. And let's just go ahead and comment this out. See if we get the same result here with our alias fib. And I'll go ahead and remove that here, give it a compile. And we are. Okay. So, you know, didn't even have to come in here and, you know, make sure that we do this twice, right? Because this is just a function, taking an input and output, just like we started with today. Okay, folks. So another really cool thing with the D programming language, to just have this built in and not really have to worry about it. Just import the standard functional library. And again, you know, if you're not used to or don't know about this idea of memoization, then, you know, you've got a new topic that you can explore in computer science. That's super, super cool, where you trade a little bit of space, potentially saving lots and lots of time, and Fibonacci being a classic example of this. So with that said, if you are trying to keep track of all the cool things in the D programming language, you can check out my page at courses.msha.io. Keep track of your progress here. The D language here is free. I've got other courses you might want to check out otherwise. But with that said, folks, thanks for your time and attention. Hopefully you enjoyed this video, and it's very appropriate that we're getting some recursion there. Here, get rid of that. I'll leave that in because I feel like it's only appropriate if we have, when talking about Fibonacci and how bad recursion is, that we get some recursion. See, there we are again. Anyways, folks, thanks for your time and attention, and I'll look forward to seeing you in the next lesson.